Okay, so welcome back for section 6.6. In section 6.6, we're going to take a look at the math that we're going to be using for the sample p-hats as approximators for population parameters. Okay? And the reason it's going to work is because, well, basically it's a trick that we're going to use where population proportions and sample proportions, p's and p-hats, can be thought of as the results of binomial distributions. So in this session, we're going to take a look at how the math of a normal distribution as an approximator to the binomial probability distribution plays, and then we'll take a look at how that would work out for the idea of p-hats and p's. Okay, so here's the math behind it. If you have a binomial scenario with given probabilities for P and Q, where P is the probability of success and Q is the probability of failure, a sample size of n, and if your sampling is sufficiently large enough. Now, sufficiently large enough means that both n times P and n times Q are both 5 or more. That is, the sample size times the probability of success, n times p, and the sample size times the probability of failure are both bigger than 5, then you can use a normal distribution to approximate binomials with the parameters that the mean of the normal distribution is n times p, and the standard deviation of the normal distribution is the square root of n times p times q. Right? We do have to make something called a continuity correction to make the math work, because binomials are discrete in nature. X is 1 or x is 2, but it can't be 1.5, whereas normals are continuous. So to convert a discrete to a continuous, we have to do something called the continuity correction. Okay? So just to review, binomial probability distributions are ones where we have a fixed number of trials. The trials are independent. We look at everything as success or failure, and we have all of this notation right here, where n is the number of trials, x is the number of successes out of those n trials that we're looking for. We have little lowercase p for the probability of success in a single trial, and q is the probability of failure, and that q and p are complements of each other. That is, that p can be found by taking 1 minus q, or q can be found by taking 1 minus p. Right? And then if your sample is large enough, if your sample size is sufficiently large enough, that is that n times p and n times q are both bigger than 5, then we can use a normal distribution as a modeler, as an approximator for our binomial distributions. The only thing we have to do is we have to do something called the continuity correction. And what the continuity correction does is it takes a single value x that is a discrete whole number and makes it into an interval by taking the lower end of the interval down by 0.5 and the upper end of the interval up by 0.5. What that means is, if my job was to find the probability that x is exactly 5, when I turn that into a normal distribution, I'm going to find the probability that 4.5 and 5.5 are the range of values. Right? I'm taking a value and turning it into an interval by adding to the upper end of half a unit and subtracting from the lower end. Right? If I had something more complicated, like if I was trying to find the probability that 3 was less than or equal to x was less than or equal to 5. When I convert that, that 3 is going to turn into a 2.5, and that 5 turns into a 5.5. Right? So the lower always goes down by half a unit, the upper goes up by half a unit. And this is because discretes are being modeled by continuous distribution. And so we have to convert discretes into continuous. Okay? Let's take a look at an example and see what we can come up with. All right? In a survey of 1,002 people, 701 said they voted in a recent presidential election. The voting records showed that 61% of eligible voters did vote. Given this value, 61%, find the probability that among a random sample of 1,002 eligible voters, at least 702 did vote. Okay, so this is binomial in nature. We have a sample size of 1,002, right? We have the probability of success, the probability that they did vote, of 0.61. We have a probability of failure of 0.39. Okay? And x could be anything 0, 1, 2, 3, all the way up to 1,002. The probability they want us to calculate is the probability that x is at least 701. Okay? Now what I'd like to do is I would like to convert this problem from a binomial problem into a normal distribution problem. Okay? Now in order to do this, I need to make sure that, first off, that my problem is binomial, and we've already established that, and two, that my sample size is large enough. That is, I need to check to make sure that n times p is greater than or equal to 5, and n times q is greater than or equal to 5. Now, given that n is 1,002 and p is 0.61 and q is 0.39, it's going to be very easy just to go 1,002 times 0.39. That's 390. That's way bigger than 5. And 1,002 times 0.61, that's 611. That's way bigger than 5, so we're good there. So both of these are acceptable. So then what we can do is we can turn this into a normal distribution problem where we're going to find a probability of being bigger than, here's where the continuity correction comes in, 700.5. Where did 700.5 come from? Well, if 701 is a lower limit, I take lowers down by 0.5, I take uppers up by 0.5. So since it's a lower limit, we go down by half a unit, 701 minus 0.5, 700.5. But in order to do a normal probability calculation, I need to have a mean and a standard deviation. Well, the good thing is when you convert a binomial to a mean, a binomial to a normal, the mean is just n times p, which we've already got. It's sitting over there on the calculator at 611.22. Okay. And we also need a standard deviation. Our standard deviation is the square root of n times p times q, which I don't have written anywhere on the screen. I'll figure that out when I actually get to the calculations. At this point, now I just need to go ahead and do this calculation. If my job is to find this right tail here of a normal distribution, I'm going to go back to my distribution menu, do a normal CDF. I'll put in my lower limit. I'll put in my, wait, there is no upper limit, so I just put in a big number. I'll put in my mean, which is 611.22. I'll put in my standard deviation, so that's going to be the square root of n times p times q. Close those parentheses. Paste it back in. Run the calculation, and I get, what did I get? Well, I got a statement that says the probability that x is greater than 700.5 is, let's see, 0.1, 2, 3, 4, 5, 6, 7, 8, 4. That's supposed to be a 4. Let me fix that so it looks more 4E. Huh. That's essentially 0, isn't it? So the probability that if only 61% of the voters voted, that 701 people who said they voted actually did vote is so small that it makes me think that something's wrong with this problem. Either the people who said they voted actually didn't vote, or maybe the 61%, this assumption that was made, is false. And so we think back to the last session. Remember where we talked about someone making a claim, gathering data to test that claim? The claim here would be that that 61% is true. And if we assume that that is true, that this value of 61% is true, then what does our data show? Does our data support that claim being true? Or does our data not support that claim being true? Because if our data supported that claim, then getting a sample with 701 people voting should not be a rare event. And this looks exceedingly rare. And just, there's not an error in our math here. That is the actual correct answer for this problem. So this math right here is how we're going to use binomials as a way to test population parameters of a population proportion against a sample statistic of a p-hat. So someone is going to make a claim. In this case, the claim here is that 61% of people voted. We're going to go gather some data. Our data is that of 1,002 people in our sample, 701 said they voted. Does the 701 support that 61% is true? Or does the 701 give us evidence to support that 61% might not be true? Okay. Now, I know there's another option here. The other option is people are lying. And yes, that does happen. We'll talk about that more when we actually start doing our hypothesis testing. All right, let's take a look at another example and see. A study on aggressive driving found that 47% of drivers say they have yelled at another driver. You randomly select 200 drivers in the United States and ask them whether they have yelled at another driver. What is the probability that at least 100 drivers will say yes? Okay, I'm seeing binomial here, so I'm going to go grab that binomial data. I got a sample size of 200. According to the data, 47% should be success, which means that 53% should be failure, and X could be anything 0, 1, 2, all the way up to 200. The probability that they want us to calculate is the probability that at least 100 drivers will say yes, that X is greater than or equal to 100, at least 100. Okay? I want to convert this to a normal probability distribution. So that means I want this guy again. So I need a mean. Well, my mean is always n times p. In this case, that's going to be 200 times 0.47. And I need a standard deviation. My standard deviation is always the square root of n times p times q, which in this case is the square root of 200 times 0.47 times 0.53. Okay? This 100 is a lower limit, so that's going to be 99.5 or higher for our interval. So we're going to find the probability that X is greater than 99.5. Okay? Now, one thing I didn't do is I didn't do the check. I know that I'm supposed to check every single one of these to see that n times p and n times q are both greater than or equal to 5. But when I looked at these numbers right here, they're both like a half. And half of 200 is so much bigger than 5, I actually just didn't do the math. I just trusted that it was going to be big enough. Right? All right. So now that I converted it from a binomial to a normal, I'm going to go ahead and do that calculation. So I'm going to go to my distribution menu, normal CDF, lower limit, 99.5, no stated upper limit, so just a big number. Mean of 200 times 0.47. Standard deviation of the square root of 200 times 0.47 times 0.53. paste it back in, and I get 0.2179, or about a 21.79% chance of 100 plus drivers saying yes, they have yelled at another driver. Okay, so 21.79. That's not low enough for me to think that the claim of 47% is not true. Right? I went out and got a sample to test the claim of 47%. Right? That would be what I would be doing here if this was a hypothesis testing problem. And that's not a small enough percentage to say, data doesn't support it. I would have to argue that my data supports it. All right, last problem, and then we're going to be done with Chapter 6. A study of the National Football League retirees aged 50 or older found that 62.4% have arthritis. So there's our claim that someone's making. You randomly select 75 retirees and ask about whether they have arthritis or not. What's the chance that exactly 48 will say yes? Well, that sounds very binomial to me. So let's gather that binomial data. Okay. Our n is 75. Success is 0.624, which means that failure is 0.376. X could be anything from 0 to 1 to 2 all the way up to 75. They want us to calculate the probability that X is exactly 48. Now, I know that there's at least one person watching this video who's like, couldn't we just do that with the binomial formula? You absolutely could. You could do all these problems with the binomial formula. This isn't about whether you should use the binomial formula or the normal. This is building a skill that we're going to need in the next section, the next couple chapters, so that we can do this. Right? So if you're looking at this going, why wouldn't I use the binomial? If all you wanted was the answer to this question, use the binomial. I'm just doing this as a preparation for what's coming. Right? So I'm going to convert this to a normal distribution problem. Right? Our mean, n times p, so 75 times 0.624. We're looking at 46.8. Our standard deviation, square root of n times p times q. Whatever that works out to be, I'm not going to figure it out. I know that my middle is about 40, and they want me to find the probability that it's exactly 48. So my middle right there is that 46.8. So 48's over here somewhere, but I have to turn it into an interval. So how do I turn a single number into an interval? Well, I'm going to make that then be 47.5 to 48.5. So if I just have a lower limit, or if I just have an upper limit, I take it down by a half or up by a half. But if I just have a single value and I want to turn it into an interval, the way that I turn it into an interval is I have to make the bottom go down by a half. So 48 down by a half and 48 up by a half. Okay. At this point, it's just a matter of punching some buttons on the calculator. So normal CDF, lower limit of 47.5, upper limit of 48.5, mean of 75 times 0.624. Standard deviation of the square root of 75 times 0.624 times 0.376. Close those parentheses. And I get that this is equal to 0.911, or 9.11%. So there's a 9.11% chance that if I talk to 75 NFL retirees, that exactly 48 will say yes. If I had done this using the stuff from last chapter and just done it directly as a binomial with 75 and 0.624 and 48 and just ran it that way, look at the answer I get. 0.0198. So instead of 9.11, I would get 9.18%. These are pretty close together. And in statistics, we would argue that they're close enough. We're what, 0.07 off. The difference between these two numbers, if I take that one and subtract off this one, is a very, very small number, 0.0007 rounded. Okay. It's not a significant amount of difference, which is why we love this normal approximation technique. Okay. All right, that brings us to the end of chapter 6. So I'm hoping that it worked for you. Have a great day, and I will see you all back here for chapter 7.